Section 13.4, Motion in Space. Suppose a particle moves through space so its position vector at time t is r of t. Then we define its velocity pretty similarly to the way we did before as just the derivative of position, r prime. Notice that we're using r instead of s to be consistent with our vector notation. The speed of the particle at time t is the magnitude of the velocity vector, that is, the length of v of t. As in the case of one-dimensional motion, then the acceleration of the particle is defined as the derivative of velocity, which is in turn the second derivative of position. So let's do an example and find velocity, speed, and acceleration when t equals 1 and illustrate this geometrically for the curve given by r of t equals t cubed I plus t squared j. So first let's get velocity, which is the derivative of position, r prime. So that's by the power rule, just 3t squared I plus 2tj. And let's get acceleration now. So that's just the second derivative of position, and that's 6ti plus 2j. Now let's find the speed, which is the magnitude of velocity. So that's the square root of each of those components squared, so it's square root of 3t squared, and then I need to square that, and I'll add that to 2t squared. So that simplifies to 9t to the fourth plus 4t squared. And I'm supposed to find all of these at 1, so the velocity at 1 is 3i plus 2j. The acceleration at 1 is 6i plus 2j. And then our speed at 1 is the square root of 13. Okay, let's see if we can illustrate this now. How about I try sort of drawing what our position curve looks like. It's this interesting kind of shape, sort of like that. And I would like to draw velocity, so I'll use another color. Let's say here's the velocity at 1. So I should probably indicate that this is the point at 1, so that's 1, 1. And let me also draw acceleration. So how about this vector over here for acceleration? Let's find the velocity, acceleration, and speed of a particle with position vector t squared e to the t e to the t. So first, velocity. Pretty much the same as it is before, except that I just have an extra dimension, but not a big deal. We just do the power rule, and then derivative e to the t is e to the t, and then for t e to the t, we have to use the product rule. So doing that, we should get 1 plus t e to the t when we simplify. And then acceleration is the derivative velocity, or the second derivative position, however you want to think about it. So that's 2, and then e to the t, and then 2 plus t e to the t. Again, you have to use the product rule and simplify. Then if I want speed, that's the magnitude of velocity, and that's the square root of 4t squared plus e to the 2t plus 1 plus t squared e to the 2t. And if I wanted to draw this, they didn't tell us to, but we could. It's pretty similar to our two-dimensional case, except that I'm just going to throw in a z-axis, something like this. So let's say here's at 1, and let's say here's my curve, something like that. And let's do velocity. So how about that for velocity? And acceleration similarly will be that. And those are both the acceleration and velocity at the value 1. Okay, how about finding velocity and position given acceleration? So in this case we have to work backwards. So let's start with velocity. We can find that by integrating the acceleration, just like before. So that's the integral of 4ti plus 6tj plus k. And that's just going to be equal to 2t squared I plus 3t squared j plus tk. And because this is an indefinite integral, I need a constant. But I have to be a little bit careful here. My function gives us vectors. So in this case, the constant is a constant vector, c. And I would like to figure out what that constant vector is, so I'll use the fact that they gave us the initial velocity, v0. They told us it was I minus j plus k. So we have v of 0 equal to I minus j plus k. So that means that, well, notice if I plug in 0, this disappears, and this disappears, so I just have c. So v of 0 must be c. So c must be equal to I minus j plus k. So I can now I have a complete formula for the velocity. It's just 2t squared I plus 3t squared j plus tk plus I minus j plus k, or for our constant c. So what we can do is we can group together all of the i's. So that's 2t squared and 1. So that's 2t squared plus 1i. And then similarly for the j's, we have 3t squared minus 1. And for the k's, it looks like we just have t plus 1. Okay, so for velocity, I just need position now. So do the exact same thing again. R of t will just be the integral of v of t. So that's just the integral of 2t squared plus 1 I plus 3t squared minus 1j plus t plus 1k. And that ends up being 2/3 t cubed plus t I plus t cubed minus t j plus half t squared plus tk when we take our antiderivative. However, like before, we need a constant. We already used c. We're using k for our vector k, and it's probably not a good idea to use a capital K because it looks so similar. So how about we use d for our second constant? And similarly to the way that we solved for c, we could solve for d. They gave us r of 0 as the vector of 1, 0, 0. So that's the same as saying that r of 0, our initial position, is I. Just 1i, 0j, 0k. So again, you plug in 0, this disappears, this disappears, this disappears. So that means that r of 0 must be equal to d, so d must be equal to I. So we can complete r of t just by throwing in an I. So let's do that. We get that r of t is 2/3 t cubed plus t, and then we'll throw in one extra I, so plus 1. And the rest stays the same. T cubed minus t j plus 1/2 t squared plus tk. So the technique we used in the previous example can be used in general. Whenever we have acceleration, we can find velocity. Whenever we have velocity, we can find position. We just have to add our initial velocity to whatever we integrate for acceleration, and we have to add our initial position to whatever we integrate for velocity. And that accommodates for the vector constants, as we saw c and d. Also, if the force that acts on a particle is known, the acceleration can be found from Newton's second law of motion. The vector version of this law states that if any time t, a force f of t acts on an object of mass m, producing an acceleration a of t, then f of t must be equal to that mass m times the acceleration. So let's do an example of that. Say we have an object with mass m that moves in a circular path with constant angular speed omega, and it has position vector a times the cosine of omega t I plus a sine omega t j. Let's find the force acting on the object and show that it is directed toward the origin. So first let's get to v of t. That's just the derivative of position. So that's, let's see, derivative of cosine is minus sine. So we'll just use the chain rule. Omega is a constant. So this is like taking the cosine of 2t. So it just becomes minus a times omega times the sine of omega t I. And similarly, we'll do the chain rule again for this guy. Omega hops out in front, and we get a times omega times the cosine of omega tj. So let's get acceleration now. Acceleration is the derivative of the velocity we just got. So that's just another omega hopping out in front by the chain rule again. So that's minus a times omega squared cosine omega ti minus a times omega squared times the sine of omega tj. Just realized that we're using a over here as a constant, but a over here is the vector. Not such great notation, but that's okay. We'll be careful, keep our arrows so we don't get confused. Let's get the force vector now. So our force is mass times acceleration. So we just throw an m in. So that's minus m times omega squared. And I can factor out because I've got omega squared in both of these guys. So multiplying by m, that'll also come out. And I've got left inside a times cosine of omega ti plus a sine omega tj. But this is kind of cool. Notice that our position was given by this. A cosine omega ti plus a sine omega tj. So that means that we could write the force as just minus m times omega squared times position. So the force vector is basically the position vector, except that it goes backwards. The position vector pointed towards a circular path. So that means that this points the opposite way. It points inward from the circular path towards the origin. So I can draw this, hopefully, let's see. Make this y, this x, and how about I make this r. Oh, that was bad. It was almost good, but okay. Let's say that's our circular path. Let's say this is just some point P on the path, and let's say that the radius of the circle makes an angle theta. Well, then our constant omega would just be d theta dt, but that's not really that important. What's important is seeing our force. So how about I use this for force? I'll draw a bunch of the, remember, it points outward for the position that I drew to draw the circle. So the vectors pointing inward are our force. So these are all our force vectors. And obviously there's lots more of them, I'm only drawing a couple. But for every single point in the position that you get, every single point along the circle, you get another one of these force vectors. Remember, the way that we make our curves is we have some vector, it points to a point, and then it points to another point, and then it points to another point, and it points to another point. And what we have here is the force just being the same thing, but they're in reverse. It is minus something times the position, so instead of pointing out, it just flips that vector and points in. So we call this a centripetal force with a T, which means center seeking. Say a projectile is fired with angle of elevation alpha and initial velocity v0. Assuming that air resistance is negligible and the only external force is due to gravity, let's find the position function r of t of the projectile. What value of alpha maximizes the range, which would be the horizontal distance d traveled? So how about we start with our force? So that's equal to mass times acceleration. In this case, we're directed downwards due to gravity. So this is just going to be equal to minus our mass times gravity as a vector, so that's gravity times j. Because remember, j is the vector that points, well, it usually points up along the y-axis, but because we're throwing in a minus, it'll point down, and it'll point down as much as gravity makes it. Remember that rg for gravity is, or the force for gravity, the acceleration due to gravity, is the length of the acceleration vector, 9.8 meters per second squared. So this means that our acceleration can be given by minus g times j. So we can integrate to get velocity. So let's do that. Our velocity will be minus gt, because g is some constant, we just throw in a t, j, and we need some constant vector. So let's see what the constant vector is. Well, remember, that constant vector is just the initial velocity, v of 0, which they told us we should use v0 for. So let's just make that v0. So that means that we now know what our velocity is, so let's get position. So we could write the derivative of position is v of t, which is minus gtj plus v0 instead of c. So that means that r of t must be equal to minus 1/2 gt squared. Go backwards again with the power rule. And t v naught plus some constant d. So again, our constant d is our initial position. So notice we're starting over here at the origin. So our initial position is the 0 vector. So that means that we now have a formula for position. R of t must be minus 1/2 gt squared j plus t v naught. Let's see if we can write this vector v naught a little bit more explicitly for our position function. So remember that the magnitude of v naught, our speed, is some constant value. So how about we just call that v naught without the arrow? This is a scalar and this is a vector. So we'll abuse notation a little bit. We'll have to just be careful to remember the difference. So this means that our vector v naught can be given in terms of its speed using trigonometry. Let's go back to our picture for a second. Here's our vector v naught. If I were to draw, let's say, a triangle, notice that I can get this adjacent side because the cosine of alpha is adjacent over v naught, adjacent over hypotenuse. So that means the adjacent side must be v naught times the cosine of alpha. And similarly, the opposite side, the height, is v naught times the sine of alpha. So I can write the components in for v naught now. It's v naught times the cosine of alpha I plus v naught times the sine of alpha j. So that means that I could write r of t in terms of the initial speed, v naught, and the angle too. So v naught cosine alpha t plus v naught sine alpha t minus 1/2 gt squared j. Notice I grouped together the j terms. So how about we write parametric equations too? This tells us that x would be v naught cosine alpha t and y is v naught sine alpha t minus 1/2 gt squared. Notice this kind of makes sense because if you eliminate the parameter here, which we won't bother doing, eliminating t, then you actually get a quadratic equation, which is a parabola. So that makes sense for the position. Let's see if we could find the value of alpha that maximizes the range. Let me go back for a second. Notice that we want to maximize this distance over here, which is the x value when y is 0. So let's plug in y equals 0 and see what we get. We should get a value over here, which we'll disregard, and we'll get a value over here that maximizes d. So if we plug in y equals 0 to our position function, let me go up a little bit, then we get either t equals 0, right? If we plug in y equals 0 for this guy, either t is 0 or t is equal to 2 times v naught times the sine of alpha divided by g. Because if you plug that in, then everything cancels over here. So that means that our distance d, which is our x value, is v naught cosine alpha, and then times this t value of 2 times v naught sine alpha over g. So we've got v naught, so that's v naught squared. And then we've got 2 sine alpha cosine alpha over g. And if we want, we can use our trig identity. Remember, 2 sine cosine is just sine of 2x, or 2 sine x cosine x is sine of 2x is a better way to say it. So this is just sine 2 alpha, and then over g. So it looks like we want to maximize d, so d has a maximum value when this numerator is the biggest. The biggest value for sine is when sine is 1. So sine is 1 at 90 degrees. So that means that alpha should be 45 degrees to give us 90 on the inside. So we have our maximum distance at an angle of 45 degrees. Say a projectile is fired with muzzle speed 150 meters per second. So that'll be our initial speed, the initial magnitude of velocity, and our angle of elevation 45 degrees, so that's alpha, from a position 10 meters above ground level. So we have to change our ground level a little bit. Where does the projectile hit the ground and with what speed? So it looks like because of this 10 meters above ground level business that our initial position shifts. So our initial position is no longer the origin. It is instead 0, 10. So we'll just have to move y up 10 when the time comes. Let's put in our other variables. We've got 150 meters per second for v naught. We've got 45 degrees for alpha, which is our maximum distance, so that's good. And we've got our acceleration due to gravity as 9.8 meters per second squared. So from before, we have x equals v naught cosine alpha t, so that's 150 times the cosine of 45 degrees times t, which is 75 rad 2t. And then for y, we have to be a little bit careful. Everything is shifted up because our initial position is 0, 10. So we'll just add 10 to 150 sine 45 t minus half gt squared, which is 9.8 t squared. So we get 10 plus 75 rad 2 t minus 4.9 t squared. Again, let's see where it hits the ground, so that's where y equals 0. So that means, well, how about I set this equal to 0, but then when I want this coefficient to be positive, so I'll just divide everything by minus 1. So that's 4.9 t squared minus 75 rad 2t minus 10 equals 0. So we'll use the quadratic formula to solve this thing. We get t equals 75 rad 2 plus the square root of 11,250 plus 196 all over 9.8. And that ends up being about 21.74. So let's get x now. So x is about 75 rad 2 times 21.74. Now that we know what our t value is. So that means that it's about 2306 meters. So that's where the projectile hits the ground. Let's see if we can get the speed now. So to figure out with what speed, we will first need velocity. So that's our derivative of position. So that's just 75 rad 2I for our x value when we take the derivative, and then 75 rad 2 minus 9.8 tj. The length of this vector is, well, we'll also take it at 21.74, and the length of this vector is just going to be our speed at 21.74, so that's 75 rad 2 squared plus 75 rad 2 minus 9.8 times 21.74, and then square that, and that ends up being about 151 meters per second. So that's our terminal speed. If we use this scalar v to represent the magnitude of the vector v, in other words, the speed of the particle in motion, then we can write the acceleration in terms of its components using a unit tangent vector and a unit normal vector. So our picture kind of illustrates how this would make sense. We have our normal vector going in one direction, which gives us one component for our acceleration, and we have our tangent vector in the other direction, so that gives us our other component. We just have to make sure that we scale the normal by some, scalar, and scale the tangent by some scalar. So it turns out that those scalars are the v prime derivative of speed, and kappa times v squared, the curvature times speed squared. So to prove this, we'll write our unit tangent as what its definition is, derivative of position over the length of the position vector. And derivative of position is just velocity over the magnitude of velocity. So that's just velocity over this scalar v that we used for notation purposes. Okay, so that means that we can multiply both sides by speed, and we get that velocity is equal to speed times our unit tangent. Acceleration is the derivative of that. So we can take the derivative using the product rule, and we get that that's just v prime times our unit tangent plus v times the derivative of the unit tangent. We also know that curvature kappa is written as the length of the derivative of the unit tangent over the length of the derivative of position. The derivative of position is just the length of the derivative of position is just that speed. So that means that we can multiply kappa by v to solve for this length of the derivative of the unit tangent. So we get that length of the derivative of unit tangent is just kappa times v. Then we use the definition of the unit normal. That's just t prime over the length of t prime. So now we substitute in. We have that t prime by itself, you just multiply through by the length of t prime, is the length of t prime times n. We said that the length of t prime was kappa times v, so we substitute that in. So now we have that acceleration is v prime times t. That's what we already had. We also had it was v times t prime, but we know that t prime is kappa vn, so we just have v times kappa v, which is kappa v squared n. So we managed to prove it. Just a bunch of confusing notation, but otherwise not that bad. Turns out we can also rewrite the tangential component, normal component for our acceleration, just in terms of derivatives of our position function. This should make sense because notice this formula over here looks very similar to a formula we had for curvature. So you can already see how this is going to come about. To prove this, we take the dot product of velocity and acceleration. So that's just vt dotted with our formula for acceleration. So we distribute the dot, and we get that v prime times t dotted with t plus this thing dotted with t. Remember that t and n are perpendicular, so the dot product is 0, so that just disappears. And t dot t is the length of t squared. Length of t is 1, it's a unit tangent. So all we have left is v prime. So then we have the tangential component for acceleration as v prime. So that's just going to be this v dot a divided by v, as we just showed. And v dot a is just r prime dotted with r double prime. And v, the way that we said, was the length of the velocity vector, which is the length of the derivative of position. And we do the same thing for our normal component. That's just kappa v squared. So kappa we have a formula for. We plug that in. V squared is derivative of position squared. We take the length. So that cancels 2 of these guys. And just leaves us with the formula we wanted. So let's do an example real quick. We've got position function t squared, t cubed. So let's find the tangential and normal components of acceleration, at and an. So we'll start with our position function. So let's write it in terms of ijk. It's t squared I plus t squared j and t cubed k. So our derivative, r prime, is just 2ti plus 2tj plus 3t squared k. R double prime we're also going to need, and we'll have to take the cross product, of course, but first we get 2i plus 2j plus 6tk. So we also need the length of r prime. It's basically like when you're cooking and you get your mise en place. We're just getting all this stuff out of the way. So that's going to be the square root of 8t squared plus 19 to the 4th. I made this too long. Okay, so now that we've got all our ingredients, let's get the tangential component. So that's just r prime dotted with r double prime over the length of r prime, which is pretty easy to compute because it's a dot product, not a cross product. So the dot product is just 8t plus 18t cubed, and we got the length was the square root of 8t squared plus 9t to the 4th. Alright, now we need the cross product for the normal component, so let's do that. R prime cross r double prime. Well, that'll be I, j, and k in our matrix, and then 2t, 2t, 3t squared, and then 2, 2, and 6t. And then we'll take the determinant. So for I, it looks like we get 12t squared minus 6t squared, so that's just 6t squared. And then for j, we get 12t squared minus 6t squared, so that's 6t squared, and then we throw in a minus because it's j. And then for k, we have 4t minus 4t is 0, so we don't have any k. So it looks like our normal component will be r prime crossed with r double prime. We take the length of that, and we divide it by the length of r prime, So that's just 6 rad 2 t squared. We take the length of this divided by the square root of 8t squared plus 9t to the 4th.